Hello, welcome to the Advanced Undergraduate Intermediate Graduate series on Calculus of Variations. This lecture is the first one deriving Euler-Lagrange equations for particular Lagrangians. In this case, the Lagrangian is a function of one variable t. We'll later deal with ones that depend on more than one independent variable. But this is the function that we'll be looking at today. It's a very, very common one in physics. So this class of functionals is defined by an integral for t between 0 and 1. And it's a function of y of t, where y of t is a vector-valued function in a vector space. The vector space is those functions that map from A, B to Rn, where each of the components yi of this function are C2. So long as we stick with that vector space, then I don't have to worry about technical things. So we've got this functional. I don't know what L is, but it has arguments, y arguments, derivative of y arguments, and t possibly explicitly in there. The admissible variation set is going to be all the y's in that vector space that have fixed boundary conditions. In other words, at t equal to a, y is equal to the vector a. At t is equal to b, y is equal to the vector b. As such, the admissible variation space, A star, is a subspace of this thing, of V rather. And the subspace is, as it's defined here, where at the endpoints, eta, which is a vector-valued function, is equal to 0. And at the right endpoint, it's 0 as well. Remember that we have to keep these two things separate. So A is the space of admissible functions. That's what we're minimizing over. A star is the set of admissible variations. And what that means is that if I take a y out of this set of A and I add to it any eta in A star, then the sum will also be in A. That's the defining property for A star. So we're going to compute the first variation of the functional, j. And we're going to do this for a general Lagrangian L. So L has got, again, so j at y plus eta will be L evaluated at y plus eta epsilon eta in this first argument, and then y dot plus epsilon times eta dot, and then possibly t. Okay, so I want to find a power series of this thing, and in particular I want to find the first derivative of this thing in epsilon. So what's happening here is we're fixing y, we're fixing eta, and we're letting epsilon, which is a real number, vary. And we're going to take the derivative of that capital F of epsilon in epsilon and evaluate at 0. Astute observers might say, hey, what happened to the extra term in here that was minus j of y? Well, we're going to be differentiating in epsilon, so that term is always going to be a constant, so we only need to look at the derivative of this first thing. Okay, so that being said, the general theory says that this expression in blue that I'm highlighting right now has to be true. What does it say? It says the first variation in j at y in the direction of eta, defined to be this derivative at 0, has got to be 0 for every single admissible variation. That's if we want y to be an extrema. Min, max, etc. So to take the derivative of this j, you just have to look and see where epsilon sits. Epsilon sits in this argument here. and epsilon sits in this argument at the top of 2. So when I differentiate this whole thing in epsilon, I can bring a derivative in epsilon outside into the integrand by making it a partial derivative in epsilon. That's a calculus result. So if I do that, I'll take the derivative in the y arguments times, with the chain rule being, times the derivative of this thing in epsilon. And then I'll have a derivative of L in the y dot arguments times the derivative of this thing in epsilon as well. So what you get when you do that and you set epsilon equals 0 is you get the partial of L in each of the y's times a to I. So these are the components now. This is Einstein notation. If I write this out, this means a sum from I is equal to 1 to n. So I sum these products. So this is really a representation of n terms representing the n partial derivatives in y. And there's going to be n arguments for yi dot, and times the derivative of the y dot argument in epsilon gives you the a to I dot. So I've got this first form of this expression, and I'm going to try to set it equal to 0 eventually, but before I do that, we're going to do an integration by parts. Why? I want to get rid of this thing here. So what the goal here is, I want to have things that are multiplying the etas, but not the etas and the eta dots. So if I do that, this term will have a minus d by dt of those terms. And then there'll be a boundary term when you do integration by parts, and that'll be simply this first, it'll be this term without the dot on the eta evaluated at t is equal to a and t is equal to b. Namely, so when I do integration by parts, there's a boundary term plus something times a to i's, and this is an implied sum over the i's. So if this is, I'll have a y1 term here times an a to 1 plus a y2 term times an a to 2, etc. And this boundary term, as I just said, it's this expression here evaluated between t is equal to a and b. Now, before I move to the next slide, I'm going to point out something here. Eta is in the set A star, and A star has eta equal to 0 at both of these endpoints. So it's because of that I get this next expression. Since eta vanishes at the endpoints, the boundary term really is just 0. So I'm left with the first variation of j at a y in the direction of eta is equal to something, in parentheses, times a to I. And this integral has to vanish for every single eta. So now it's at this stage, there would be you'd be naive to say that, oh, just because if this thing equals 0, that term there must be 0. It is true that because this is true, it is equal to 0 for all etas, that this term in the parentheses vanishes. But that's the consequence of continuity. It's not an algebra issue. You don't just say, oh, I cancel the etas and I get this thing equal to 0. What it is that this expression in here, it's whatever it is, for whatever your L you've got, and however complicated this thing is. The thing in parentheses is, I'm going to call it a little f. And so it's a function of t, whatever it is. You put a y in, it's a function of t. And then I've got it multiplied by another function, I'll call it g of t, where g of t is arbitrary but continuous. There's a theorem that in analysis that says if a continuous function times an arbitrary continuous function integrates to 0 for all those arbitrary c's, then this function f must be 0. That theorem applied to this expression says the term in the parentheses here that I'm trying to highlight must vanish. Well, that's the result. If this term vanishes, I'm going to state this is a theorem. If L is C1 in its arguments and Y, which is a vector valued function, extremizes J, then that can only be true if the Euler-Lagrange equations below are true. What are they? You take L, partial derivative in yi, equal to the total derivative in time of the derivative in the yi dot terms. This is not one equation. This is actually n equations. And it's a set of n equations depending on what your L is initially. I could be 1. So this might just be one equation, but I could be 1, 2, 3. So that I'd have I is equal to 1, 2, 3. I'd have 3 coupled equations then. So this is a compact form. Now, the easiest example to show you first is the case where I is 1. So I'm going to say that this is just going to be a scalar function. It's not going to be a vector valued function. So we want to take a look at that case. So for that case, the Euler-Lagrange equation is this thing up here. It's the partial of L in y evaluated as arguments is equal to d by dt of the partial derivative of L in y dot. That's one equation for y of t. It's a differential equation. Let's see how this pans out. So restating the functional then, where I just have y and y dot. I don't have yi's in there and yi dots. So I just have a y and a y dot. And I've got it fixed at both endpoints. Then there's this lemma that helps us solve this differential equation. There's a couple of scenarios. Suppose this function L does not have y occurring in explicitly. Imagine a formula as complicated as it is, it's got t's and y dots, but no y's explicitly. That means the partial of L and y is 0. Well, if the partial of Ly is 0, that's 0 in the Euler-Lagrange equation above. It would be 0 is equal to the total derivative of something. That means the something has to be a constant. That's what this says. So if L of y is equal to 0 in this Euler-Lagrange equation, you get this thing called a first integral. So I've got one arbitrary constant. And if you look at this and you put in the explicit dependence of y and y dot in there, this really is a first order differential equation with an arbitrary constant c. So that is not too hard to solve. Sometimes you can't solve it, but many a times you can. There's a different kind of first integral where I get a constant of integration, and that happens when the Lagrangian here does not have a t occurring in explicitly. So if imagine, say this whole thing was y squared plus y dot squared and there was no t's, and that was all. Well, that would be the partial of L in t is 0. No explicit t dependence. I claim in this lemma that this quantity here is constant. And it has to be that y is for extrema only. So for extrema, this thing's got to be constant. So the way you prove that, all you do is you take this expression here, and shorthand notation is this, and I take the derivative of that. So that's the total derivative in t of L, that's this first expression, minus, and then I'm going to take the time derivative of this term here. Well, by the product rule, it would be y dot times the derivative of Ly dot in t plus y double dot times L sub y dot. And then I expand this thing out using the chain rule, and I get that term. And I look at that and I say, hey, there is a common term here. This one minus same thing on this side. They cancel. And what you're left with is something times Ly dot and a different thing here times y dot. So writing that out explicitly, cancel, you get Ly minus d by dt of Ly dot times all times y dot. Well, this thing is exactly the Euler-Lagrange equation. It has to vanish. By necessity, it must vanish at an extrema. So since it vanishes, I've got 0 times y dot. That's equal to 0. So what does this say? It says the time derivative of this quantity is 0. Therefore, this quantity is constant, making it a first integral. You can use these two facts to solve these simpler problems. I'm going to show you some examples. These are all examples from now on, no more theory. So suppose I had a Lagrangian look like this, and I'm doing the integral on some interval. We don't really care too much about that right now. So if this is the Lagrangian, the extrema must satisfy this Euler-Lagrange equation. So let's first take a look at this. This L has no y in it. So L sub y, the derivative in y, the partial derivative in y, is gone. However, the partial derivative of L in y dot is not 0. So here's a y dot cubed, so the partial of that would be 3 y dot squared. Partial derivative of this term here would be minus x squared times 1. So Ly dot is this expression here. And since Ly is 0 by the lemma, this quantity must be a constant. So let's recap. If this is the Lagrangian, then the extrema must satisfy this differential equation for some arbitrary constant C1. So I look at that and I think, I can probably solve that differential equation. In fact, I can just solve for what y dot is. I'll just solve for y dot. Y dot is equal to plus or minus this. So you just bring an x squared over here, bring this over there, take square roots, and this is what you end up with. Well, if y dot is that, and that's some arbitrary constant, I can merely just integrate both sides to find out what y of x is. So y of x must be plus or minus 1/3 times this thing to 3/2 plus a second arbitrary constant. So to reiterate, if the Lagrangian was this, and I'm taking the integral of it and extremizing it, then y must have this form for some constant C1 and C2. The way you find those constants C1 and C2 is you make them satisfy the boundary conditions. The y has to satisfy whatever boundary condition you're given at the left side and the right side. So that's two equations for two unknowns. We won't do that here. We'll do the second case where, here's a different example. This is a minimal surface area of revolution, and this is a formula. If I tell you what y of x is and I revolve it around the x-axis, then in first year calc you would see a formula that looks like this and says the total surface area of revolution is given by this formula. It's using method of disks. So what I want to do is I want to extremize this functional. And I'm going to say, in this case, I'll define what my admissible set is. So it's C1s, that's actually sufficient, such that at one endpoint, y at x equal to 0 is 1. And then at the other endpoint, y is some number beta bigger than 1. So whatever the shape is, it's got a narrower opening at the x equals 0 location than it does at the x equal 1 location. Since x does not occur explicitly in this, so the theorem was putting a t in here, so I can change t and make it x, and I've got a y prime, which is the same as y dot. So the theorem says that since there's no explicit x, this quantity here has got to be equal to a constant. Now, if you look at the functional dependence on this, without knowing too much, just look at L it depends on y's and y primes. And I'm going to subtract a y prime times another function that depends on y's and y primes. So the left side, when all is said and done, is going to have y's and y primes in it, equal to a constant. If I use this Lagrangian that I'm highlighting up above, this L in blue that I've got, and I put it in this formula and I do all the calculations and simplify, this expression becomes this one here, becomes this term here is equal to C1. That's a differential equation for y of x. How do we solve it? Well, much like the previous one, I can solve this by solving for y prime. I'll square both sides, bring this over, divide by C1, do a bunch of algebra, and you get dy dx is plus or minus this. All right? Now, that is a separable first-order differential equation. I can take all of this, I can go dy divided by all of this is equal to dx, and integrate both sides. So the solution depends on taking what I have here, 1 over what I'm highlighting, 1 over this, and then integrating in y. That's doable. It gives you inverse hyperbolic cosines. And so if you do that and you solve this, then y of x turns out to have this particular form. It's some arbitrary constant C1, that's that C1, that occurs here too, and then plus a new constant C2. So I've got two constants defining y of x. Let's apply the left boundary condition. Y of 0 is equal to 1. What does that give me? Well, that means if I put x equal to 1, this side here, this has got to be equal to 1 when I put an x equal to 0 on this side. And if you think about that, that tells me it tells me how to solve for C1 in terms of C2. So I do that, and I get the following expression. So having used the left boundary condition, I now have eliminated one of the unknown constants, and I still have a remaining unknown constant. But I can find it. How do I find it? Well, if I put x equal to 1 in that expression, then this y has to be beta, and that x has to be 1, and then I just got C2s in there. So another way of saying that is the C2 has to be a root of this function f, which is this function evaluated at x equal 1. So that would be this thing here. Now, you can't do this analytically, but you could draw a graph of this, and you could see that it equals some beta at some particular lambda, and you find that numerically, and you put that back into here, and you get your solution for the minima of this problem. It's very typical that when you get a form, when you're solving Euler-Lagrange equations, you get a lot of unknown constants of integration, and then boundary conditions typically, or other conditions, determine a set of algebraic equations for the unknown constants. Geodesics on a cone. What's this? Okay, I can already see a slight typo here. This y here is supposed to be y squared. So a cone has the equation x squared plus y squared is equal to some constant a squared times z squared. And you can define a cone parametrically using this and this. So if x is r cos and y is r sine, then it must be the case that z is ar. That's a parametrization of the surface, commonly called the cone. What is a geodesic? I talked about this much earlier in the very first lecture. And what a geodesic is if you fix 2 points on the surface, you're trying to find the curve on the surface that minimizes the length. All right, so I'm telling you, here's a parameterization of this surface, and I'm now going to let r be a function of t and theta be some function of t, and that'll describe a curve on this thing then. And I want to know what the length of that curve is. Well, I can't get it directly just from this. I need to know what x dot, y dot, and z dot are. Well, for x dot, you take the derivative of x in time. It's got 2 terms here that depend on time. So by the product rule, it'll be r dot cos theta, that's this thing, minus r sine theta, theta dot. That's this term here. So I just took the derivative where r and theta are functions of time. Y dot, same thing. Z dot's easy. It's just a constant a times r dot. So how do you find the length? Well, it's x dot squared plus y dot squared plus z dot squared. Take the square root, you integrate between time, and that gives you a formula here in t. Once integrated, gives you the length of the curve that is on the cone. Now, given these 3 expressions here, x dot squared is going to, I can take that and square the right side. Y dot squared, I can square the right side. And you'll notice that there's a plus and minus sign here, and I'm going to get cross terms that cancel because some of them will be minuses and some will be pluses. And then I'll also have things like r dot squared times cos squared, r dot squared times sine squared. So that'll just be r dot squared because of a trig identity. You do all that, and you get this expression here. So what is this? This is the functional that tells you the length of a curve on the cone. And the way it depends actually on 2 things. It depends on r of t and theta of t. So right at the very beginning in this lecture, my y vector could have n components. This is a case where you have 2 functions of t that you need to find to minimize this functional. So the functional depends on r of t's and theta dots of t's and r dots of t's, etc. Well, if you look at this, so I'm gonna point out one thing. Since L sub theta is 0, that means the Euler-Lagrange equation for theta is simply going to be the derivative of L sub theta dot. So since this is 0, one of the 2 Euler-Lagrange equations is going to be this thing is equal to a constant. So this L sub theta dot, that's taking this square root expression here in this Lagrangian and taking the derivative in theta dot. That only occurs in one spot in here. So I do that partial derivative, I get this expression. That's got to be a constant. I'm just going to redefine this thing here to be b squared. And then I look at this and I say I've got an expression that's actually separable. If I have this as b squared here, and what I do is I'm going to try to solve for dr d theta and then separate it, you get this. There's a little bit of algebra there. It's maybe not immediately obvious, but if you do that, basically you solve for theta dot is what you do. And there's a bunch of algebra and things will cancel, and it turns out that d theta dt is this expression before the dr dt. So, so that means on the geodesic, which is the thing that minimizes this length functional. D theta is equal to this expression in r dr. That integral can be done. Integrate this thing in theta, that'll be theta plus a constant. Integrate this thing in r, that will give me this b arcsine secant inverse of r over c. You can look in tables, that's what happens. So I solve for r in terms of theta by inverting this, and I get on the geodesic, little r is equal to some function of theta, and that function is this, where I've got c1 as a constant and c2 as a constant of integration. How do I complete it? You tell me the two starting points on the cone, and that will give me two equations for c1 and c2. So that's a slightly more complicated example, but we've just solved our first geodesic problem. Last thing I'm going to show you is this one here. This has got, this is written in the notation of what we had before. I've got a y1 squared term. I got a y1 prime, y2 prime. I've got a y2 here. So this is like a function of y1s and y2s and y1 primes and y2s. And I'm going to define the set A to be, make sure that all of these yi's are smooth functions, C2 smooth, that satisfy certain boundary conditions. A whole bunch of them are 0 on one or the other endpoint, and the only one that is non-zero is y2 of 0 is going to equal 1. The Euler-Lagrange equations are, you take this Lagrangian L, and I do partial of L in y1 is equal to partial in y1 prime times the derivative. Then I've got y2. So I've got partial of y2, and I've got derivative of the partial of y2 prime. Those are two equations which are coupled. If you do the calculations, this first equation here, so the first one, is this thing here. This is, I can just check that. Ly1, partial of this in y1. That would be partial of that in y1, which is 2y1. So there's the 2y1. Equals Ly1 prime. Well, y1 prime is here. I take the derivative in y1 prime. That will be 1 times y2 prime. So that'll be y2 prime. If I take the derivative of that in t, I get y2 double prime. So that's the writing out what the first Euler-Lagrange equation is explicitly. You do that for the second one, and you get two equations for the two unknowns. Well, this is really, if you think about it, so I've got two coupled second order equations. That's a generality. We'll see this in, if you actually had y1, y2, y3, you'd have three coupled second order differential equations to solve, which is non-trivial in many instances. In this case, you can actually solve it. How do you do that? So how do I solve this system? I guess I would look at this, and what I would do is I would take the second equation here, and I'd say I don't even need to know what y2 is. I just integrate that twice, and I get this expression here. So the second equation alone tells me that y1 is 6t squared plus c1t plus c2. So then I use the boundary conditions. y1 of 0 is 0, and y1 of 1 is 0. And when I use those two conditions, I find out that this constant is -1 and this constant is 0. So that y1 must be this expression. Once I've determined what y1 is, then I can go back to the Lagrange equation and say, hey, I know what this side here is, and I've got y2, so I do a double integration on it, and I use the boundary conditions for y2, and I find out that y2 is equal to this expression. So let's just summarize this. Here's a function of a vector-valued function y1. Y has got two components, y1 and y2. They define my Lagrangian here. For this Lagrangian, I get two coupled differential equations. Those are the Euler-Lagrange equations. So sometimes you'll have an Euler-Lagrange equation, but other times you'll have equations that are coupled. So this is the case where they're coupled. So I've got two equations. So it's a fourth order system. I solve it, and I apply the boundary conditions to find all the unknown constants. And then that gives me the y1 and y2 that extremize this functional to find using that Lagrangian.